Okay, in this video we're going to be talking a little bit about a binary tree data structure. The idea of a binary tree is basically a structure in which you have a node, which is sort of a storage structure that holds a particular value. So in this case, this node is the circle, and it's storing the value 0. So you have this concept of nodes, and they are connected to each other in various ways. So with a binary tree, the nodes are connected by a parent node, and it has two child nodes. There's a left child node that also stores a value. In this case, that value is 1, and a right child node, and it stores a value which is the value of 2 in this case. Now, these values can be anything. In this case, we've clearly started numbering. The values stored in the nodes are sort of like indexes, an index number, but that's coincidental, right? That's just so we can distinguish between the nodes. So in this case, we've arranged the nodes such that the root is 0, and we're filling the node values in order from 0 all the way up to 11, but we're filling them in the order of level, so the horizontal level, and then from the left to the right. So once we complete one level, we go down and we fill from the left to the right. And once we fill that level, we come down a level and fill from the left to the right. Okay, so a tree that's filled out in this manner is called a complete binary tree. Now, the binary portion of this, why is this called binary? It's because of the number of children we allow. So if this node is a parent node, it has 2 children, right? This node is a parent node of these 2 children. This node is a parent node, but it only has a left child. We don't have enough nodes to fill in the right child. So a complete binary tree is a binary tree in which we've filled out one level at a time, left to right, and it's okay if there's empty space or empty nodes at the bottom layer, but no other layers can have empty nodes. Like we couldn't just remove node 6 and still call this a complete binary tree. Now, a perfect binary tree would have all the layers perfectly complete. Okay. So again, the major takeaway though, binary tree, there's 2 children. There are lots of different tree structures in computer science and math. All sorts of theory around math use lots and lots of different types of tree structures. We could have 3 children or 4 children or any number of children allowed, but there are some special properties of the binary tree that are very useful in computer science. So we're not going to go too much into the use cases. We're just going to really start exploring this data structure, how you can store data in this way, and how to sort of manipulate this type of data structure. Okay. So what we want to do first is think about how can we store data in this structure. All right. So the easiest way would be to have a list of data. So we could have a list of numbers 0, 1, 2, 3, 4, 5, right? And that would be our data, and each position in the array would sort of be like our node. But we'd have to calculate, like if we have a particular node here, say we start at the root node. So the root node is always at the top of the tree. This is a parent node, but it's not a root node, right? So if we start with the root node, and we have a list of data, how can we get to its left child? And if we have the index of the root node, how can we get to the right child? Right? What about any other node? Let's say we have this node. This is the index 4. Right? So how would we get to the left node? How would we get to the right node? Well, if you look at this, there's a little bit of a pattern, right? If we double the index value and add 1, it's the left node. If we double it's the index for the left node. If we double the index and add 2, it's the right node. So let's see if that follows in all cases. Double 1 plus is 2 plus 1 is 3. 2 times 1 is 2 plus 2 is 4. So 2 times 2 plus 1. So you add 1 for the left node. That's 5. 2 times 2 plus 2 is 6 for the right node. So you always add 2 for the right, and 1 for the left. So we can try another one. 2 times 4 is 8 plus 1 is 9. 8 plus 2 is 10. So there's this pattern, and of course it involves the number 2. right? Because this is a binary tree. There's good reason why it involves the number 2. Right? So we have sort of structured this visually. We've structured this. This node has an index of 0, 1, and 2, and there's also some value associated with it. Right? In this case, the value we're storing is just the same as the index number for simplicity. And this allows us to generate simple lists in Python, and we can use those lists to sort of manipulate, this sort of data structure. All right, so what do we mean by that? Let's take a look at this. Let's start digging into binary trees a little bit. So we're going to call this one bintree underscore list.py, and we're basically going to create tree data, and it's going to be an empty list, and we can make a loop for I in range and however many number of data points we want. So we could say we want to start at 0 and go to 15, and then we're going to say tree data append I. Okay, so this is sort of a longhand version of creating this, and we can just print that out to start with. Tree data. All right, and this is, oops, let's see, Python 3, bintree list. Okay, so that's our list. Now I do have a helper function here that's going to allow us to print this form of data. So basically each one of these positions is the node, and the value we're storing in here, it just so happens that the values are the same as the index numbers for this list. But we could have anything in here. We could have alphabetical characters, we could have objects, we could have any number of things. But this is strictly, we're using numbers here strictly so we can understand the index numbers when we print this out as a tree. So I have a helper function here called bintree print, and we can briefly take a look at that. So if you need to, you can pause. This isn't the prettiest, most elegant thing. I've used this in a lot of different places and sort of just tweaked it as needed, so it's probably not super efficient. But what this does, it allows us to print out a tree structure on the terminal, and so we can look at this. So if you want to, you can pause it and you can copy this down. I'll try to add this code in the comments, but again, it's sort of messy, but it works. So here we're going to go back to bintree list, and we're going to from bintree print, we are going to import this print list tree. Okay, so we have a tree that's made as a list, so we're going to import print list tree. All right, and then we can now I'm just passing in the data array tree data. All right, so this gives us a visualization. So here's the actual data structure we're using to represent our tree, and then here's sort of a callback to this image, right? This sort of style. We have a root node, and then there's an implied in the terminal. There's an implied connection here between 0 and 1, and 1 and 3 and 1 and 4, and then the left child of 2 is 5, the right child of 2 is 6, right? So you can kind of imply those connections even though they're not actually there in the terminal. All right, we also have some additional information over here. We have the level number, okay? And in computer science, generally the numbering starts at 0, which is why the first value here we're using index 0. So we're also going to use the first value for the level as 0 just because it's common in computer science. So this level, there are patterns, right, that we see here. The first level has 1 item in it. The second level has twice as many as the previous level. So there's 2 items. right? So the next level has twice as many as that, right? Which that makes sense because the parent always has 2 children. So however many nodes you have, there are going to be twice as many on the next level. So each level is going up by 2. So again, we have that concept of 2 flowing through this entire data structure, a binary tree. All right. So if you wanted to know how many items were in a particular level, it would be 2 the base. So the number the style of tree that it is, it's a binary tree, so it's 2 to the level power. So 2 to the 0 is 1, 2 to the first power is 2, right? And then 2 to the second power is 4, 2 to the third power is 8. All right. What else can we look at this binary tree and see? Well, what about each level is the same number, so each level has the same number of items as the entire tree before it plus 1. Right? So this level, it has the same number of items as the entire tree before it, which is 1 plus 1 more. So 1 plus 1 is 2. So this row has the same number of items as the entire tree above it. So that's 1, 2, and 3 plus 1 more. So this is 8. Right? There's 8 items here. And 4 plus 2 is 6, plus 1 is 7. 7 plus 1. Okay, so there's some interesting mathematical relationships that we need to be aware of and be considering as we look at this tree structure. All right, so let's say, generally speaking with these tree structures too, is you have a concept of a node and you need to be able to traverse from this node to this one, or from this node to that one, and this node to one of its children, right? There's an implication of being able to transition, right? That's what these lines sort of represent. So if I were started at index 0, I would need to find the index of the item for the left node. I would need to find the index for the item at the right node, etc. Right? So I'm going to need some functions to help me calculate that. We already discovered the sort of relationship that we need. So we're going to need to get the left index and get the right index. So the left index is 2 times the current index plus 1, and the right index is 2 times the current index plus 2. Okay, and this all depends on how you start your numbering. We're starting with an index 0. If we started numbering at 1, it wouldn't be the same thing, right? So keep that in mind. But there's still a very similar pattern. All right, so binary tree, we want to define a function get left index, and we're going to pass in an index, and the result is just going to be 2 times that index plus 1. And then define get right index, we pass in index, return 2 times index plus 2. So nice and easy. We have some helper functions here that will help us sort of navigate the tree implied by these connections, right? Now again, we're not actually physically storing this tree in a manner that these connections actually exist, right? There would be a way to do that. We could create a node class, and we're probably going to do that here at the end. Create a node class and then a tree class and actually connect those nodes together with memory references. But we're not doing that here. The way we're storing this is just as an array, and the actual connections, right? So these lines here don't actually exist in our program. They're theoretical, and we have to calculate them. So they're abstract. The concept, there's no actual connection in the way we're storing this data. So we just have to theoretically figure out what that would mean. You know, how to get the next item to the left, or the next child, the left child or the right child. And to do that, we're calculating that index. All right. Okay, so when we look at these binary trees, one of the main thing we're going to be going over today is how to traverse them, how to travel through the data in different ways. Okay, so if you have this tree structure and you want to print out every single node, or the value of every single node in this tree structure, there are various ways to do that. All right, the simplest way, starting out, especially considering the way our data is stored, would be what's called a breadth-first traversal. Now these are all called traversals. When you're printing out the data of all the nodes in a binary tree, it's a traversal of some kind. So breadth first means you are printing out level by level, and on each level left to right. So sort of the way that they're numbered by default. So we can see here that breadth first is going to be very easy for us. That's the simplest type of traversal because we have the underlying data structure is just an array or a list, and the items are just stored like that, one after the other. Okay, so this is going to be by far the easiest method. Okay, so we want to define a function, and we'll say this will be I guess we don't need a function. We'll just say print breadth first traversal. All right, and then for I in range length of tree data, that's going to give us an index for our data. And again, we need the index in case we decided to store something else in tree data. Like I could, in tree data, I could, we could convert this to letters instead of numbers, and we'll do that here in a second. So breadth first traversal for I in range length tree data. I want to print out, I'm going to use a format string here. I want to print out the tree data at index I, and then I'll put a space, and then the end character for this print is empty space, so that way it's not printing out a whole bunch of lines down the screen. It's just going to print one thing, and then the next thing, and then the next thing, all in one line. And then when I'm finished with that, I will print the new line. Alright, so let's take a look at this breadth first traversal. So this is our binary tree, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So that looks good. So what are the other types of traversals? Okay, so this next type of traversal actually has 3 different variants. So this is what's called a depth first traversal. Okay, depth first traversal. So what do we mean by that? The idea of a depth first is instead of going row by row and completing the entire breadth of one row or one level, right, the breadth of the level, we're going all the way down depth of the tree as far as we can go, and then we'll come back up, and if we can go down further the other side, we'll go all the way down as far as we can go. So by default, we'll go left as much as we can, and if we can't go left, then we'll go right, but then we'll keep going left, right? So left, right. So always go left first, then once you've gone left, you go right. But even if you've gone right, you still go left after that if you can, and then once you've done that, you go right. So you never go right until you've already gone left. That's the basic idea of this depth first traversal. Right? So this is called, in the depth first traversal, when we are this idea of moving from one node to the next and one node to the next here, that's called visiting. We're visiting this node, visiting these nodes in order. Now, the reason this traversal has 3 different variations is because you can print in 3 different spots in terms of your visitation of the nodes, right? So the 3 different types of visitation are this would be the preorder traversal. And then we would have an in order traversal. And then we would have a post order traversal. Okay, so there's three: pre, in order, and post. So that implies a before something, in the middle of something, and after something. Right? So what does that mean with respect to our code? If we look at our diagram here, when I visit a node, there's three positions in which I could print out the value. I can print out the value as soon as I visit the node, before visiting either of the other two nodes. So this would be the pre-order. You print out this value before visiting the children. So I'd print out a 0, then visit left, and then I would immediately print out a 1, then visit left. Then I would print out a 3, then visit left, print out the 7, visit left, there's nothing there, visit right, there's nothing there, go back up, visit right, immediately print out the 8, visit left, nothing, visit right, nothing, go back, and then visit right, print out a 4, visit left, print out a 9, nothing, nothing, go back up to 4, visit right, print a 10, right? And we would continue this way. We go all the way to the root, and then we would continue to the right. But the key takeaway is that we are printing before we visit either of the children. So that is pre-order, before visiting the children. In order would be you visit this node, and then you would visit the left child, and when you come back to this node, that's when you print, before visiting the right node. Okay, so it's in between visiting the left child and the right child. And then post order would be you visit both children. You have to visit both children before you print out the value. Okay, so we can sort of think about how we might do this. And if you think about it, recursion seems to be a good technique here. Okay, because we have the concept of a node value, and we might want to visit this node, do some stuff, and then visit that node. So we visit this node, and we might visit a whole bunch more, many more nodes, and then eventually come back. So this is really a perfect case for recursion. And generally speaking, when you have some sort of binary tree or some sort of tree structure, the recursion can tend to be a good solution. But you have to be careful, because sometimes, like in the example of the Fibonacci sequence, it actually, if you have the wrong implementation of recursion, it can actually be wildly inefficient. All right. So anyway, we're going to look at how we can do this. Let's make a recursive function called depth first traversal. So I guess what I could do is under preorder traversal, I can define a function, depth first traversal, and we'll just start out rather simply, and we'll have an index to start with. And then what we're going to do is, this is recursive, so we want to sort of, at some point we're going to get the left child and then the right child, right? So we're going to need to visit the left child. So underscore left child equals. So this is the left child index, right? So left index. All right, so we have a function for that. So whatever index we start with, and we'll start with 0, but whatever index is passed in, we can calculate what the left index is using our function, get left index, and we'll pass in our index. And then also down here, we're going to need to get the right index, the right child index. And we can do that with get right index. Okay. Now, at some point, we are going to need to visit these two locations. Right, so we need to visit the actual function call itself is essentially a visitation of a node. So this is the depth first traversal, and we pass in an index, and the process of executing this function is a visitation of that node. So what we want to do here is say if L index is less than the length of our tree data, then we recurse, right? We visit that left index. We have to check to see if that left index is in there, right? Because we get into a situation here where, you know, if we're at this value here, is there a left, is there an item at the left index, right? There is not. Right, and there's not an item at the right index. So we have to check to see if that data is there first, and if it is, then we'll go ahead and visit, because we always visit to the left child first. So DFT, so this is the recursive part. We're recursing to index. But it's not index, right? It's the left index. Alright, and then the other visitation is the same exact thing. If our index is less than the length of our tree data, then we will recurse to our index. Okay, so these are our two visitations. All right, and eventually we will get to a point where, let's say, we get to the bottom, and so these are sort of our base cases, right? So if left index is less than the length of the tree, then we recurse. Otherwise, we don't recurse, right? So these are kind of the opposite of our base cases. So if both of these are false, then we'll just exit out of the recursion, right? So now we have the two visitation cases, and so we can look at this and we can say, if I were to print the value stored at this index, this would be sort of the pre-order traversal. Right, so I could do that. Let's do that. We'll print format string tree data, and we're going to print out index. And then a space, and we'll have the end character string. Okay, so this should be a pre-order traversal initially. So we have to call that. So we're going to do that. We're going to say DFT, and we're going to start with index 0 because that's the root of our tree. Right? Again, our tree is just stored as the list, so the root item is the very first item in that list. So what would we expect here for a pre-order traversal? We would expect to see 0, 1, 3, 7, and then 8. So let's take a look. It's going to do the entire list, but let's see if we're close to that. Pre-order traversal 0, 1, 3, 7, 8. 0, 1, 3, 7, and then go back up to 3, go to 8, 4, 9, 10. Alright, so there's one problem here. We don't have that print at the end. Right, but you see how that's different than the breadth first traversal, or the pre-order traversal. And we have these other traversals as well, but they're all sort of related, right? So if we look at this again, we see that if I print it before I visit the left child and the right child, right, that's pre-order. If I printed in between those visitations, that's in order. And if I printed after, that would be post-order. Right? So instead of making separate functions for all of these, I can just sort of add a type here. And I can say, you know, that type is going to be either pre-order in order or post order. There we go. And I'll do something like that. So just so you know what values are valid there. And so then in this case, for preorder, I will say if type equals preorder, then we do this. Right? And then when we recurse, we also have to pass in the type. Right? So that way we always print out preorder. Right? If the type is originally preorder, then all of the following recursive calls will include the type of preorder. And so we do this on the other recursive call as well. Type. All right, what this allows us to do here, I forgot the colon there. This allows us to do is call depth first traversal, and we're gonna call preorder. All right, so nothing changed, so that means it worked. One thing we do want to sort of change here is we probably want to combine, we might combine this label. If the type is preorder, we might want to print that out. And then we're also missing sort of that print at the end. The problem with this recursive function is because it's used repeatedly, there's nowhere in this function that I can just print an extra new line, right? Like I have to manually do that here, right? And similarly, I have this extra print up here. I'm going to move that down here. So we have these three lines that are all sort of, that need to be executed for every single one of these traversals. And the only thing that I need to know about it is preorder, right? That's the only thing that changes, because here I'll need to know if the type is in order, and then I'll print this label and then an extra print statement. So basically I want to create an initial wrapper around this recursive call. So wrapper, I mean like a wrapper function. It wraps around it. It basically initializes this function call, but it adds in this print at the beginning. Then it will call the initial recursive call like this, and then it will add the print at the end. Okay, so this is just going to be a, I'm going to call this define DFT. And we're going to have the same stuff here, index and type. And the recursive function now is going to be called underscore DFT. So you're not supposed to call this directly. Whenever you see the underscore in front of something, generally speaking, that tells the developer, don't call this directly. So this is sort of reserved. But this is the recursive function we're going to be using, and this is the function we use to initialize the recursive call. So in this case, we're taking this stuff and we're putting it in here, right? So we can just copy all this and paste it. And instead of preorder here, we can make this a format string, and we just put in type. So whatever type we put in here, that's going to be the label. And then also, that type we can pass into our recursive function. And DFT now, this is initializing the actual recursion. So the underscore DFT is the actual recursive function. This just initializes it. This just prints something before it, runs the whole recursive algorithm, and then prints something afterwards. So this is something you'll see commonly with recursion. You'll have a wrapper function around the actual initialization of the recursive call. All right, so what this allows us to do is we can get rid of these labels, and down here I can just call DFT starting at index 0 and say preorder. Okay, and you see that gives us the new line character that we need. All right, and if I implement in order and post order, right? So remember, the only difference between preorder, in order, and post order is where you print out the value with respect to your visitations. So this is the left child visitation, and this is the right child visitation. Alright, so in order is basically the same idea here. If type equals in order, then we print it out. Alright, so we just copy and paste. Otherwise, down here, if type equals post order, we can print it out. And then we just print out. We just run our 3 recursive algorithms, or our 3 recursive calls. Now remember, DFT is the initializer to the recursion. This function does not recurse itself. It calls the first iteration of the recursion. So the underscore DFT is the actual recursion here. And again, you'll see that commonly. Okay, so we take a look at this. And we have these different traversals. So a pre-order traversal we saw, that looks like 0, then you visit the left child, 1, then you visit the left child, 3, 7, 8, 4, 9, 10, 2, 5, 11, 12, 6, 13, 14, right? But this is different than the in order traversal. In this case, we would visit 0, but we wouldn't print it out. So visit, 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 nothing to visit. 7 is the first one. So we see 7 is the first one in the in order traversal. When we go back and we can print out 3 now because we visited the left child. So we see 3 is the next one. Then we can visit to the right, visit left, nothing, print out 8. So 7, 3, 8. 1, 9, 4, 10, 0, 11, 5, 12, 2, 13, 6, and 14. All right, you see how these are ordered differently than pre-ordered. Each of these are slightly different. Now the post order is you have to visit both of the children before you can print out the value. So here, visit, 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 7, visit, 8, 3, visit, visit, 9, visit, visit, 10, 4, 1, visit, 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 11, 12, 5, 13, 14, and then 6, 2, and 0 would be the last one because you have to visit all of the other nodes in order for you to be able to come back and get to this one. Okay, so this is a sort of idea of traversals. It's different ways of navigating through trees, and this just sort of gets us started thinking about the binary tree data structure, looking at some of the patterns. One other thing we want to do here is, let's say instead of having the numbers 0 through 14, we could have anything we wanted in here. I could start this out at 97 is the numeric value for the lowercase a character, so I could just convert that into a character and run this again, and now we have values here that are letters, right? And we still have the traversal. Okay, so we can still think about these nodes in terms of their index value, right? And even though we change the actual value stored in the list to character data, there still is an index associated with it, right? The index is still 0. right? But the actual value stored there is something else, right? So learning about binary trees for computer science is very important. There are lots and lots of very good uses, efficient searching, sorting, all sorts of good stuff. Okay, so this is just basically an introduction to get you thinking about binary trees, and this is the simplest way to sort of store the data in terms of a list and just calculating the index value. In the next video, we're going to do something. We're going to create the same exact scenario, except we're going to use a class structure with nodes, and the nodes actually do have references to their left children and their right children. All right, so hopefully this was informative and you learned something. Thanks for watching.